Hello everyone, my name is Trevor May. I am the VRF and Ductless Split Technical Specialist here at Standard Air Lite. And what we're going to be talking about today is our Ductless Advanced Operation and also the Ductless Service Tool training. This is going to be specifically focusing on understanding the advanced operation of the ductless system as a good foundation, and then getting into understanding what the service tool is and what we as technicians can use out of the tool to benefit from it. So first, we're going to start off and get a good foundation in the ductless advanced operation. This is just to ensure that everybody has a good fundamental of what data the tool is going to be showing them. Because without that knowledge, essentially, we're just looking at data that we don't understand. So it's extremely important to understand first what you're looking at and then use this tool to be able to benefit from it. Okay. After that, we're going to go ahead and get into the introduction of this ductless service tool, what it is, how we can benefit from it. We'll talk about different features of the tool and different submenus that we can get into, depending on how we're trying to utilize this tool, whether it's from a maintenance standpoint, whether it's from a troubleshooting standpoint. We'll look at some of the different installation and configuration parameters that we can set up on this, namely being trying to get into troubleshooting with the E1 codes. We can get into the parameter setting where we can test individual components of that outdoor unit to ensure that they're responding properly from the command sent from this tool. And then finally, we'll get into some basic troubleshooting with the tool and understanding what the tool can and can't do and how it makes our lives easier having this tool from a service or troubleshooting perspective. Okay, this ideally is going to be about a 2-hour workshop on here. And of course, any questions, obviously, because this isn't a live situation, you can always contact myself or any of the guys in the technical service department with any questions that you may have on this tool. So let's go ahead and dive in. So first, we're going to start off with the ductless advanced operation. So first and foremost, regardless of whatever class I'm doing, whether it's the service tool class, an installation class, or a service class, anything technical related, I always like to start off and make sure that everyone has a good understanding of where our temperature sensors are in the ductless system. Okay, so in the indoor unit, if you have a true ductless system, which means a true ductless indoor unit, a high wall, a cassette, a horizontal ducted, floor consoles, underceilings, true ductless indoor units, not hybrid scenarios where we're taking a residential fan coil and bridging it with a ductless outdoor unit. So this is true ductless one-to-one or true ductless multi-link systems. All of those indoor units have two main sensors. The first one is T1, and that is your return air sensor or the room temperature sensor. The other sensor in that indoor unit is going to be your T2, which is your indoor coil temperature sensor. For example, the T2 sensor in operation for heating mode, when the system first fires up, you often hear me, if you're troubleshooting with me over the phone, or if you're attending one of my other classes, you'll hear me refer to the anti-cold air function on the indoor units, specifically in the heating mode. So essentially what that is that the indoor unit is looking at this T2 or this indoor coil temperature sensor to look at it. Once it reaches a certain degree, it'll initiate a low fan speed. Once it hits a secondary degree, a medium fan speed, and then what I call the target value or the final temperature that it needs to hit before it releases out of this anti-cold air function, you'll see the louver open up if you have a louver, or you'll see that fan speed start to increase either to your setting, or if you have it on a specific fan speed, whether it's low, medium, or high. But this sensor essentially is what's going to govern that, and the whole reasoning behind it is so that as soon as the system has a call for heat, that we're not blowing cold air on the customer. When the fan starts running is when that warm air is going to be coming out, satisfying that. And of course, the T1 sensor on there is going to be measuring room air to make sure that we're not overheating and that we're not overcooling the space, and we're meeting exactly what the customer wants out of that system. In our outdoor unit, we have 4 main sensors. We have our T3, which is our outdoor coil sensor. We have our T4, which is our outdoor ambient temperature sensor. We have our T5, which is our compressor discharge sensor. And then finally, on the multi-zone style systems, we have a T2B sensor, and this is on the outlet of the EXV. And essentially what this T2B sensor does is it takes an average between, depending on how many zones you have that are actively running, and generates a target temperature, which in turn will control a specific position or a minimum position of that EXV. Okay, we'll get into that in a minute and how that affects oil return and also the minimum position by using that T2B sensor on the multi-zone style systems. So getting into the basic operation. So for those of you that have troubleshot with me over the phone, or for those of you that have attended previous service or installation classes in the past, you'll hear me talk about running frequency. But one thing specifically that I wanted to focus on was the running frequency, and more importantly, what it is and understanding it, but also looking at the target frequency, something that this tool enables us to see what that value is. Okay, and a lot of times when I start talking about the algorithms, everyone's head seems to spin. Okay, so we need to look at this from a basic standpoint. We're not talking about how to write algorithms or understand algorithms. What we know as service technicians is we know that we can have voltage in, voltage out. We also need to have an understanding of what that board is accepting as far as information and what response it's going to give based on the information that's received. We as service technicians can check that and verify that, and with an understanding of how that algorithm or control process or set of rules is configured, we can essentially assume what that process is going to be once the information is received and what command we're going to get out. So diving into the running frequency. The running frequency is the current RPS, or revolutions per second, often referred to as well as hertz or frequency, that the compressor is running. So this is based on multiple factors. So we look at this as being, as the load increases on the system, the running frequency or the speed of the compressor is going to increase as well. And opposite of that, as we have a decrease in load, the running frequency is also going to decrease. This is often seen on the multi-zone pieces of equipment with a digital display on them. As soon as you turn them on, you'll see a 0, 0 on that digital display. Essentially, all that is a standby mode. As the system starts up, you'll see that number slowly start to climb, and that ultimately depends on how much load is calling in the space, whether it's every unit or whether it's one unit. How far are they away from set point? What is the EXV position? How long has the system been running for? There's a lot of different factors that the outdoor unit or the control looks for to determine what the running frequency of that compressor is going to be. But for us as service techs, understanding that number is essentially looking at that number, and that's the speed of the compressor. So as the load increases, the number increases. As the load decreases, the number decreases. Now looking at the target frequency, this is the pre-programmed value in the EEPROM, or the main chip of the board. Now that main chip of the board, or the EEPROM chip, is the brains of the operation where this algorithm or set of rules is stored. And essentially what this is as the sensors report information back to the board, this is the part of that board that receives that information and makes a decision based off of what information is sent to it, so that it can control various parts of the outdoor unit and also communicate with the indoor unit. Okay, so that EEPROM chip is going to be on that outdoor main control board. So when we look at that as the system is being satisfied, the compressor will adjust its speed to meet this set number. We often refer to this as the sweet spot of the system. Okay, so if we have, let's just say, a system that's starting up and we have 4 indoor units that are calling, they're all roughly about 4 to 5 degrees away from set point. Okay, as they draw closer to set point, we're going to have our running frequency slow down or decrease. Okay, and again, like we talked about with the running frequency, as the load decreases, the running frequency decreases. As all of those units start to get closer to their set points, the system is now going to look at the target frequency to run the compressor. And this is for 2 reasons. One of which is going to be maintaining a minimum flow to flush oil back through the system and into the compressor so that we don't starve it. This is also going to be at the sweet spot to maintain its energy efficiency, because we know with the inverter compressors, we can modulate the speed, and it's much more efficient to slow the compressor down and run at a lower frequency, or the sweet spot that we're talking about, than shutting the compressor off and turning it on, shutting it off and turning it on. Even with the inverter style, it's much more efficient to ramp it down versus off and on, like the traditional fixed speed system. This target frequency is pre-programmed from the factory, and in my experience, I haven't had a circumstance yet where this target frequency needed to be adjusted, but it is nice to know what that target frequency is and to confirm that the system actually is maintaining down to the target frequency. And this is something that we can have access to with the tool. Okay, so that's going to be the major differences, and also a good understanding of what running frequency is versus a target frequency. on an inverter-based compressor. So taking a look at our first temperature sensor, which is going to be our compressor discharge temperature protection. This is going to be our T5 sensor. So when the compressor's discharge temperature protection rises, the running frequency is limited according to the following rules. So essentially what that means in layman's terms is as that temperature on the T5 starts going up to a certain degree, the system realizes that and says, hey, I'm getting too hot. I'm going to throw countermeasures. Do I need to slow the compressor down? Do I need to increase or decrease fan speed? Do I need to adjust my valve positioning or my EXV positioning at the outdoor unit to try to bring that temperature down to protect that oil from carbonizing? Okay, so we look at the set of rules on there. If that T5 sensor, that discharge temperature protection sensor, reads 221 degrees and is less than or equal to the T5 less than 230 degrees. Okay, so if it's reading 221 degrees and it's less than 230 degrees, the running frequency of the compressor is not limited. It's fine. So essentially what this first bullet point is, if it's reading 221 degrees, it's not throwing any countermeasures. However, it does know that it is raising in temperature, but it has yet to throw a countermeasure to try to bring that down. Okay. If that T5 sensor is reading greater than 230 degrees, the compressor will decrease that running frequency to a lower level every 2 minutes. And like I stated before, it realizes that 230 degrees, okay, I need to throw countermeasures to bring the temperature of that compressor discharge line down. Am I going to limit the running frequency of the compressor? Do I need to adjust valve positioning, outdoor fan motor speed? And essentially these countermeasures are happening every 2 minutes, and it's going to sample that T5 sensor again after it's made a decision to see if it actually was able to bring down the temperature on that T5 sensor. If that T5 sensor reads greater than or equal to 239 degrees for 10 seconds or longer, the compressor will shut down and does not restart until the sensor reads 194 degrees or lower. And essentially this is to protect that oil, because at 239 degrees and above for long periods of time, we can start to break down that oil or carbonize it. And essentially we're going to contaminate the system if we get that oil too hot. And of course, the system is going to be pretty much a total failure once that happens. Okay, so the whole goal of the sensor is to try to protect the oil from overheating, breaking down, and carbonizing. And this is the main purpose of the sensor. The system has intelligent technology built in to try to throw countermeasures to prevent this temperature from reaching that point. However, even if it goes through its countermeasures and it can't bring down that discharge temperature sensor, it's going to kick off on a T5 code or a compressor discharge temperature code on there. And again, that system will not try to restart until that sensor reads 194 degrees or less. Another common question that I get is, what is the delay on the compressors? So the compressor restart delay has 2 rules on there. So the compressor takes 1 minute to start up from the first time, or the initial startup. Further restarts take 3 minutes. So we have a 3-minute delay before the compressor is going to restart. So don't assume as soon as you turn something on that it's immediately going to fire off, especially if it just came out of a cycle, or if you cut power on the system to take some readings and then returning it back on to try to recycle the system to see how it's operating. Understand that there is a delay to protect that compressor, just like we have on a traditional style system. So the next one we're going to look at is our indoor coil temperature, which is our T2 sensor. So we call this the anti-freezing protection. So when that T2, or that indoor coil temperature sensor, reads less than or equal to 39 degrees for a 4-minute period, or T2 is less than 32 degrees, the indoor unit capacity demand defaults to 0, or in layman's terms, it shuts down. Okay. Essentially what it's doing is it's looking at that T2 sensor and saying, hey, if my reading is less than or equal to 39 degrees for 4 minutes, the system realizes that it's tried to throw countermeasures at it and it can't do it. Or if that sensor reads less than 32 degrees, the system realizes that that, of course, is our freezing point. We don't want to freeze that indoor coil. The system shuts down as a preventative measure. Okay. After it shuts down, that outdoor unit will resume normal operation when that T2 sensor reads 46.4. We'll just keep it, we'll round it down to 46 degrees. And the protection time is not less than 3 minutes, which we know is the protection time for the compressor once it shuts off. So it's looking for that T2 sensor to read 46 degrees or greater before it restarts after shutting down this particular indoor unit on a temperature sensor code. Most of the time, this is not the case because the unit will throw countermeasures, whether that's adjusting fan speed or adjusting the EXV position to try to bring up the T2 sensor. So just like we had on our T5 sensor, the T2 sensor also has countermeasures to try to raise that indoor coil temperature. Okay, and again, it's looking at that T2 sensor, and if it does notice that that T2 sensor is starting to cool off at that 39-degree point, it's going to throw countermeasures. However, if it cannot bring up that indoor coil temperature sensor for this example, which would be 39 degrees for a total of 4 minutes, or that sensor is reading less than 32 degrees, we're going to shut the unit down as a safety to prevent any frosting from occurring. And of course, as the frost dethaws, causing any water damage in that space for the homeowner, depending on if it's in the bedroom, the living room, or above something that might be valuable to them. Okay, so we look at the rules for operation for oil return. This is usually another common question that comes up whether I'm on site or during classes. So we look at oil return being a fixed period of time where the compressor has been running at a part load scenario or that target frequency. So what we're going to do is we're going to take that compressor running frequency, and if it remains lower than the set frequency or the setting time, which is typically about half an hour, that unit is going to raise the frequency to the frequency set, or that we talked about that target frequency for the setting time, and then resumes the former frequency. So what that really means, and all the mumbo jumbo of that actual description, technical description of it is that when the unit has been running at that target frequency or lower for typically about 30 minutes or more, it's going to adjust its valve positioning and speed up the compressor to try to flush oil back to the compressor for typically about a 3 to 4 minute time period. And that usually is enough because we don't have a dedicated sensor just focused on oil lines. We're just using our outdoor temperature sensors and our indoor temperature sensors for coil temperature to dictate a low oil situation for a time where we've been running at part load and we need to start recirculating oil back because there could be a potential starving situation for the compressor. So the EXV will continue at 300 pulses while the indoor units maintain their operation. Okay, which means when it goes into an oil recovery mode, if they're all in heat, they're going to continue to stay in heat. However, the EXV, if it's at a lower pulse, let's just say, for example, while it was running in normal, it was at 250 pulses, and it goes into an oil recovery mode. The only difference is that now it's going to open up to that 300 pulse. So essentially, we're opening up the valve, the compressor frequency or the running frequency increases to try to flush that oil back to that compressor. So that EXV continues at that 300 pulse position while the indoor units maintain their operation. They will not shut down. If the outdoor ambient temperature is higher than the set frequency during the oil return, that unit stops the oil return process. Okay, and that's where that T4 sensor comes into play for the outdoor coil temp or the outdoor ambient temperature sensor on how we would stop an oil return process if it didn't run the 3 to 4 minute time period that we're trying to flush that oil back to the compressor. All right, so we look at this compressor on here and we say, okay, you know what? I'm not really getting how the oil recovery process works. So let's break it down as basic as we can. If we're running at part load for 30 minutes or more, the compressor frequency is raised to the target frequency or higher depending on what it needs to be at. The EXV goes to 300 pulses while the indoor units maintain their operation. Again, this is to flush that oil in the system back to the compressor so that we're not starving them. This oil return process can take roughly about 5 minutes to complete. One way you can confirm that an outdoor unit is in an oil recovery operation is if you look on your digital screen where we can see our running frequency, you'll see an RO on there that will alternate between the running frequency and this RO. And this essentially indicates to you that the system is in this oil return process. Once you stop seeing that alternating flash between frequency and RO, you know that the system has come out of this oil return process or oil recovery process and is back to its normal operation. So let's talk about the hot topic, especially with this year. Defrosting has certainly been a hot topic in 2021. So this slide is going to be extremely important to make sure that you guys understand how we initiate defrost and also how misapplication, either through oversizing or having additional auxiliary heat sources, can cause defrosting issues. So when we start talking about defrost, before we start looking at certain conditions that need to be met, we need to understand that these systems must run 10 minutes in order to start this process. Oversizing, coiled up line sets, and what I mean by coiled up is vertically coiled, which essentially creates a cap tube or an oil trap. Now, if they're horizontally done, that's perfectly fine. But vertical becomes the issue, because you can create a pressure drop, like a trap, or like a capillary tube, excuse me. And then you can also have an oil trap as well with that vertical coiled up line set. Short line set runs, so minimum line set on a ductless is 10 foot. Issues with short line sets is that you can flood the condenser, and essentially it'll cause frosting of the condenser itself. So we have to maintain that minimum of 10 foot. And then of course our secondary heat sources are the most common issues that affect that unit running 10-minute minimum to start looking at the initiating conditions. Now here's the issue. The system can run 9 minutes on the first call, 8 minutes on the second call, 9 minutes on the third call. Okay, so you've had 3 calls for heat. Neither one of them have reached 10 minutes, and neither one of them have had a defrost cycle. So through those 3 cycles, we now have excess frost that's starting to build up on the coil. Okay, and this usually happens because something was either oversized and it's short cycling, or we had a secondary heat source that's taking runtime away from the compressor. Okay, ductless systems should be designed to handle the full load. It is not recommended that these be put in, especially for heating circumstances, as a secondary source, just because they require a certain amount of runtime to start looking at different control algorithms for defrost, which you can see on the left, which we'll get into in a minute. Okay, the system doesn't realize that after the first heating cycle, if it ran 9 minutes, I only have 1 more minute to run on the next cycle before I go into a defrost. Okay, it restarts as soon as it's done. It doesn't realize that it ran 9 minutes on the previous cycle. So that's why it's extremely important to make sure that we're not oversizing this, we're not vertically coiling up line sets, we're meeting the minimum for line set runs, which is 10 foot, and any secondary sources of heat are set appropriately. Preferably to not have them in the room at all, but if they are, to set them back. Make sure that the ductless system is fully handling the load. So once we meet that 10-minute minimum runtime, we have certain conditions that will start initiating a defrost. So the first one's going to be if that compressor's runtime reaches 29 minutes. So again, that takes into that 10-minute minimum runtime, but a total cumulative running time of 29 minutes. And the T3, which is our outdoor coil temperature sensor, reads less than the average generated by the algorithm. That's going to be the first scenario that we're looking at. Okay, so there's an average generated by the algorithm for that T3 sensor on there as it runs for that 10 minutes, that T3 sensor essentially has to drop below and reach that 29-minute runtime, cumulative runtime of the compressor to initiate a defrost cycle. Okay, if the compressor's cumulative runtime reaches 35 minutes and the T3 sensor is less than the average generated by the algorithm. So just like the first time, if for some odd reason that T3 sensor isn't below that threshold or that average generated by the set of rules or the algorithm on the outdoor board, or in layman's terms, that hasn't dropped below a certain degree yet, the compressor's runtime is going to reach 35 minutes. If we're going to let that system run a little bit longer, see if we can get that temperature to go down on the outdoor coil so that we can initiate a defrost. The third condition is going to be if that compressor's cumulative runtime reaches 40 minutes and now the T3 sensor reads less than 11.2 degrees for 3 minutes. So we're running much longer now, and we're saying we're not going to look at that average generated by the algorithm. We're now going to look, okay, we've been running 40 minutes. I need to see if that sensor is below 11.2 degrees for a 3-minute time period. If it is, I'm going to start a defrost cycle. If it isn't, I'm not going to initiate a defrost. And then the final condition on there is if that compressor's cumulative runtime reaches 120 minutes and the T3 sensor reads less than 5 degrees. Okay, you can see more runtime. Theoretically, the outdoor coil should be much colder, so it's going to look at that colder coil and also the runtime for the final initiating factor for defrost. Okay, so these are going to be the initiating conditions for defrost. But first and foremost, we need to understand we have to run at least 10 minutes before we start looking at that cumulative compressor runtime. Now we know what starts the defrost, and we know the minimum amount of time that we have to run before it starts looking at those conditions, but what takes it out of defrost? Okay, well, the first one's going to be if that T3 or that outdoor coil sensor rises above that average. So if we take a look back on here, we see if that sensor is less than that average, we know, okay, hey, we're going to kick it into a defrost. That same average controls as that T3 sensor rises above that average on there. Okay, so if that T3 remains at that average temperature or above for 80 seconds, that's when we're going to go ahead and consider that defrost successful and take it out of defrost to return to normal operation. Okay, so those are going to be the factors that start and stop a defrost cycle, namely being an importance on the T3 or the outdoor coil temperature sensor as being one of the factors that initiates and also being the factor that ends a defrost cycle. The defrost cycle will not continue longer than 10 minutes on their maximum, and then it will naturally take itself out. Of course, if that T3 sensor is still below that average, then it will initiate itself into another defrost cycle. And sometimes, depending on your geographical location or your weather conditions, sometimes it does take multiple cycles to initiate a defrosting condition for multiple times. Try to clear that coil off. It does happen. Not so much around here, typically the first time, but again, if we do have some kind of extreme weather event, it is certainly possible. Another really good thing that you want to educate your customers on, especially with heat pumps, because traditionally they weren't always popular in this area. They were for more areas down south, like Florida, Georgia, even in South Carolina, where temperatures really don't drop to the conditions that we see here in the Northeast. Frost is normal on the outdoor coil as it runs, of course, because we need to get that outdoor coil colder than the ambient conditions so that we can absorb heat from the atmosphere and discharge that into the space to properly warm the space as needed, depending on what the set point is. Now, if the outdoor temperature is 25 degrees, well, we know that coil is going to be colder than that, so we're going to build frost. One thing we need to keep in mind that frost is normal on there. However, if after a defrosting cycle, you're starting to see continuous frost on there where it's building up into a sheet of ice, that is considered an unsuccessful defrost cycle on there. Now, of course, it's not going to be as soon as it happens. You want to give it time because it may need to cycle into another defrost to try to alleviate any excess ice on there built up during really cold conditions. However, if it's gone through multiple defrosts and it's struggling to heating the space, that's when we will consider that an unsuccessful defrost. And then we need to start looking at multiple factors, whether we're dealing with a sensor-based issue, whether we're dealing with an application issue, or the most common one, if we're dealing with a charge-related issue, we just can't get that outdoor coil hot enough because of the lack of refrigerant. So looking at the outdoor fan motor control in the ductless systems, you'll see on here, this is essentially a screenshot out of the service manual on different initiating conditions for different fan speeds on there. So the outdoor fan control under normal operating conditions will choose the fan running speed based on that T4 or that outdoor ambient temperature sensor. Now you can see on here at 63 degrees in the cooling mode, we're going to be running that fan at a very low speed. As we increase in outdoor temperature, we're going to increase in outdoor fan speed. And of course, that is all based off of that T4 sensor. So if we have a situation where that sensor is reading improperly, we could run into a situation where we might go off on high head pressure or a P1 code. Okay, but typically that's not what we run into. It's very rare that we see that. I have very few sensors that I have confirmed with technicians in the field that have failed. Typically, there are other application-based underlying reasons on why a P1 code would happen, which would be a high pressure protection. But as a basic rule of thumb, this is what we're looking at for T4 sensing conditions to initiate different fan speeds. And essentially, it acts like a motor master. It's controlling head pressure. Okay, If we run into a situation where the feedback or the RPM feedback on the motor is out of a certain range, and one of the things I do want to mention is with the tool, we actually can see the RPM that the outdoor unit fan is running at to see if it's either too low or above a certain threshold to confirm that something's going on with that motor itself. So for the outdoor fan, if that outdoor fan speed is less than 100 RPM or higher than 2400 RPM for 1 minute, the system will display an E8 failure code, which is a fan speed out of control. Now in this case, without the service tool, we can ohm out the fan motor, we can check it to ground, we can make sure it has a secure connection, we can check the drive board that it connects to make sure that it's outputting the correct voltage, make sure that there's nothing stuck in the motor, but we weren't able to confirm what RPM that fan was trying to run at, or when it was running, was it too low or too high? And this is something with the tool we can plug in and verify. So one of the many useful features of the tool is to be able to see the RPM and confirm why that E8 code is happening on initial startup. Now we switch over and look at that fan motor in the heating mode. So just like we did in the cooling mode, we're looking at outdoor temperature to dictate fan speed. Okay, so for outdoor fan control, under normal operating conditions, the system will choose the running speed of that fan motor in heat based on the T4 sensor or our outdoor temperature sensor, just like the cooling mode. During defrost, the outdoor fan motor shuts off until the system is no longer in defrost. If your fan motor is running in defrost, we might have other issues that we need to dig into. But just like any other defrost, that outdoor fan motor should not be running because we need to get that coil nice and hot to properly defrost any excess ice buildup. Now in this case, you can see as the outdoor temperature rises in the heat mode, the outdoor fan is going to slow down. Now in this case, roughly at about 70 degrees, we're going to be running that fan at the lowest fan speed setting possible, which is our freeze fan speed. And as we decrease in outdoor temperature, so we'll look at 32 degrees, we're going to look at that fan motor running in our absolute highest fan speed, which would be at 32 degrees. Of course, as we drop lower than that, the highest we can go is a high fan speed. So anything 32 and lower, that fan should be in a high fan speed operation. Okay, same concept as the heating. We're just inversing on how that fan adjusts to high and low temperatures and what it reacts to. So we look at that fan motor in low ambient cooling mode. Okay, so the outdoor fan speed is going to be controlled now by the T3 sensor, which is the coil temperature sensor for low ambient cooling. When T4 is less than 59 degrees, and we look at T4 as being the outdoor ambient temperature. So when the outdoor temperature is less than 59 degrees and the T3, which is our outdoor coil, is less than 86, the unit enters into the low ambient cooling mode. The outdoor fan in this low ambient cooling mode now chooses a speed according to that T3 sensor or the coil temperature sensor, because now we need to take the temperature off that coil to modulate the fan speed, okay, to get proper head pressure control. Essentially, it's acting like a motor master control. So when that T3 sensor is greater than or equal to 100.4 degrees, or when the T4 sensor is greater than or equal to 68 degree outdoor temperature, the fan speed chooses a fan speed back to the T4 sensor. So what we mean is when that coil temperature is 100.4 degrees or the outdoor ambient temperature is 68 or above, it will now choose fan speed to its default operation, which is the outdoor ambient temperature sensor, and take itself out of the low ambient cooling mode. And you will see on the display that it will display that the system is in a low ambient cooling mode feature on there. And again, essentially that is to control the head pressure on it, and also what enables us to be able to operate cooling mode in low ambient conditions, typically for server room applications is where we see it most. Okay. So with that low ambient temperature protection, when that compressor is off, and the T4 sensor is lower than -31. So the system's off, that T4 sensor is lower than -31, the unit will display an LP code and will not run, which essentially means that outdoor temperature is too low for the system to run. It's going to shut it off. If the compressor or the system is running and the T4 sensor remains lower than -40 for outdoor temperature for 10 seconds, that unit will stop and display the LP code, which essentially is known to say, hey, it's too cold, I can't run, and it has a hard shutoff. When the T4 sensor is lower than minus 26 degrees for 10 seconds, the unit will restart and try to run. So what that means is that if that sensor for some odd reason was reading negative 40 for that 10-second period and shut down, when that sensor reads lower than negative 26 degrees, or it starts to get warmer outside, for 10 seconds or longer, the unit will restart and try to run. Okay, and again, by default, the outdoor fan speed is controlled by the outdoor ambient temperature sensor. During a low ambient cooling operation, it switches away from that T4 or that outdoor ambient sensor and now controls it based off of outdoor coil temperature, which essentially, again, acts like a motor master on your rooftop style unit, or a motor master if we're trying to look for a low ambient cooling operation for server room units. All right, so let's jump over to the EXV operation. So the EXV control is going to be fully closed when the power is turned on. The EXV will go through a test function and will open the valve with 350 pulses. On the multi-zone, this starts from port A and works its way up to 40, of course, depending on what model of multi-zone that you have. If it's a single zone unit, there's only one valve to go through this test function, but regardless, should have some form of clicking. A lot of the times the guys will power the unit on and they'll hear this click, 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 click. That's that EXV test function, and it's a great way audibly to see if the unit's responding properly, because if you don't hear that test function on there, you might want to start looking, is the board outputting the correct voltage to the valve to pulse it open, test it, or is there an actual issue with one of the coils inside the valve and it needs replaced? Okay, so when that EXV goes to that test function, it'll open up to the 350 pulse position, which is fully open. And then it will adjust after the compressor starts to a target angle. And again, that's going to be based off of that T2B sensor, which is on the outlet of that EXV. Okay, and essentially it's just telling it where the EXV needs to be to feed the proper amount of refrigerant to the indoor unit, depending on whether we're in heat or whether we're in cold. The EXV closes with 160 pulses when the compressor stops. Okay. So when a call for cooling or a call for heating is received, the above process is followed once again. So if you get a call for heat, call for cooling, EXV is going to go up and it's going to modulate to whatever target angle based off of the T2B or the outlet sensor of that EXV. Essentially, it's acting like a traditional TXV with an outlet sensor on the evaporator. Except now, because the EXV is at the outdoor unit, we're taking the temperature on the outlet of the EXV. And now we're going to maintain our position based off of that temperature. Okay, you have to understand in the heating mode that these do not close 100%, and that ultimately stems back to circulation of oil back to the compressor because we have multiple ports and we could pipe great distances with the ductless split system, so we don't want oil trapped out in the lines. We need to get it back to where it matters, which is at the compressor. So the action priority of the EXV is A, B, C, and D. And of course, those are all going to be your individual zones. That is the same reason that we tell you, depending on what kind of multi-zone system that you have, that your largest tonnage needs to start at port A and then work its way up, B, C, and D. For example, if you had a 2-ton indoor unit, the 2-ton should go on port A. If you had two 12,000s, they should go on ports B and C, and then the 9,000 would go on D. So start from the bottom, work your way up. The compressor and the outdoor fan start their operation only after the EXV has initialized. If for some odd reason that EXV is going through its test function and fails, or it's not pulsing at all, that compressor and outdoor fan motor will not start. That's essentially a safety control to verify that the valve can open. The board receives that command, okay, it's open, and then it adjusts the compressor and outdoor fan speed as needed when it starts up, and the valve pulses open or closed, depending on how much refrigerant is needed to be fed into that particular indoor unit. Okay, so we look at the EXV operation in the cooling mode. So the initial open position of that EXV is dependent on the indoor unit size. So it'll differ between a 9, a 12, an 18, a 24, and so on and so forth. That adjustment range for pulses is from 100 to 400 pulses. When a unit starts to run for 3 minutes, the outdoor unit receives the indoor unit's capacity demands, or the T2B sensor data, and calculates between all the zones that are connected. So if you have zones A through C connected, it's going to take an average between the T2B sensors on zones A, B, and C, and then generate an average after a certain amount of runtime. And that's going to be the target angle or the target pulse or the opening position of that EXV to maintain a minimum, or where they're going to go and rest at. It's like a sweet spot, like we talked about for the compressor. It's almost like a sweet spot for the EXV. Okay, it's going to maintain that minimum position and open and close as needed, depending on what the indoor unit running conditions and demands are. Because that capacity demand changes as we get closer to load and as we get further away from load. But that T2B sensor is one of the factors that controls that sweet spot of those EXVs are maintaining their minimum positions across there. Okay. So after comparing those T2B sensors with the average, the outdoor unit will give the following commands. If that T2B sensor reads a greater temperature than the average, remember the average generated for once it starts running for 3 minutes, it now has that average. If that temperature sensor reads greater than the average, the EXV will need 16 more pulses open. And this is how we're going to start controlling refrigerant flow to the indoor unit based off of temperature and that average generated for that first 3 minutes of runtime. If the T2B sensor reads less than that average, the EXV needs 16 pulses closed. Okay. If the T2B sensor reads an equal temperature between the sensor and the average, the valve doesn't make any position. It's exactly where it needs to be. It's doing what it needs to do based on temperature. No need to adjust it. This process is carried out every 2 minutes during the cooling cycle. This process is a direct reflection of superheat control, or the outlet of the EXV, which on average, superheat, unlike traditional systems on these, is a lot lower. We usually see it anywhere from about 2 to 6 degrees superheat, but of course that ultimately depends on a bunch of different criteria. Okay, so in the cooling mode, we know when the sensor of that T2B reads greater than the average, we need to open up that EXV and allow more refrigerant to go into the indoor unit to cool that coil down. The T2B sensor, if it reads less temp than average, we know that there's too much refrigerant going to the indoor unit, so we need to close at 16 pulses, and they always move in those incremental 16 pulses open, 16 pulses closed. Okay, so that's cooling mode operation. So now we get into the heating mode operation with the EXV. Okay, so that initial opening position of the EXV is 250 pulses in the heating mode. This too will depend on the size of the indoor unit that is connected to the system, so it varies based on tonnage. After that unit runs for 3 minutes, just like we did in the cooling mode, the system will read the T2B sensors, and like the cooling operation, will calculate an average between them to figure out what the average temperature is. If we go above it and below it, we need to either open or close the valve appropriately. So after creating this average between the T2B sensors after 3 minutes of runtime in the heat mode, the outdoor unit's EXVs will respond in the following ways. If the T2 sensor reads less than the average, the EXV will close 16 pulses. If the T2 sensor, and this one actually should be T2B, excuse that the typo on the slide. If the T2B sensor reads more than the average, the EXV will open 16 pulses. And finally, if that T2B sensor reads equal between the sensor and the average, we don't have to adjust it. That's right at that sweet spot. There's no need to adjust. And just like the cooling mode, this process is carried out every 2 minutes during that heating cycle. Okay, again, so we have to think how the refrigerant flows. So we know that the reversing valve is shifted. We're sending hot gas to the indoor unit. We're sending liquid back to the outdoor. Okay, and that's where EXV is. So if that T2 sensor reads less than the average, so it's colder, or warmer, excuse me, that EXV will close 16 pulses. Okay, if that T2 sensor reads more than the average, okay, we talk about, excuse me, we talk about being a warmer temperature. It's now going to open up 16 pulses because we don't need that indoor coil that warm. So we're going to allow more flow. Okay, it's just the inverse of the AC. Okay, so that's going to be the basic operation between the EXV and the cooling mode and how it controls. and the EXV operation in the heating mode and how it controls. All right, so we talked about the advanced service features with the ductless equipment. That should all give us now a good foundation of how the system responds to certain scenarios and how it's controlling EXVs, compressor speed, generating averages. So now we can use this ductless service tool that gives us all this data, and we can understand what that actual data is, and more importantly, what it means in terms of why the system is acting the way that it is, whether you're troubleshooting or whether you're just going through a maintenance procedure and confirming that everything seems to be running within factory parameters. So getting into the ductless service tool, your BOM code is going to be your part number for this tool. We do have this tool in stock and ready to ship out. So you can see on here, the tool essentially to me looks like a code reader for a car. And essentially that's what it is. It's going to get into the system, not only give you error codes, but it's going to give you operational information and also allow you to go in and get some functionality out of the tool as well. So you'll see your LCD screen that displays different operating menus. So it requires either a 5-volt DC power or a line voltage power, depending on whether you're dealing with a 115-volt system or a 208, 230-volt AC system to power it on. Now you'll see on the back side here, there's 2 magnet clips, which make it really nice because you could just put it right against the unit, plug into the system, and now you can start getting your data depending on what you're trying to access out of the system. The biggest thing on there with this is going to be when you're plugging in for power. I talked about the 2 different connections on there. You're going to get 2 different wiring harnesses. Connection 1 is going to be for your high voltage, or your L, N, and S, or L1, L2, and S connection. And that, of course, is going to wire on the bus bar either of the outdoor unit or the indoor unit, depending on what information you're trying to gather. Your second connection is your 5-volt connection. That's going to plug in on your main PCB board. And you'll see in this illustration, this is going to be the middle pin, or the smaller pin. So you're either using this 3-pin or the smaller 4-pin right here. The connection off to the right-hand side in this picture, we're not going to worry about. It's not applicable to this American market. We're just dealing with the LN and S, or a 5-volt communication that plugs in on the main PCB. Okay, do not connect these at the same time. Otherwise, you know you're mixing DC voltage with AC voltage in the same terminal. It's going to cause an issue and take out the tool. Okay, so before you turn power on, you're either going to choose between connection 1 or connection 2, depending on what information you're trying to access. And we'll get into that in a second on what different connections offer as far as data. Once you've got your connection plugged in, and it's either at the board or on the bus bar, you need to make sure that you choose the appropriate voltage on it. So 5-volt connection, 12-volt connection, LN and S. So we know we're either using the 5-volt or LN and S. So just set it to the appropriate configuration depending on what you're doing. From there, with the LN and S connection, you have access to self-checks, online checks. You can check an indoor PCB, an outdoor PCB for any issues. You get an indoor unit query, a target frequency, a fan speed, a T1 temperature, T2 temperature, and the mode. And that's all in the indoor unit. Now, of course, T1 and T2 is going to be in the indoor unit. You can wire this up to check an outdoor PCB, and we'll get into the different features and how you can actually set those up and run those checks on there to confirm if you actually do have a bad board or if there's another factor at play. The second connection, which plugs into your outdoor unit on the 5-volt connection, the test port pin on the board. Typically, they're a red color. I have seen them in white as well, but what you're looking for is a test port connection. So with that, you're getting your parameter inquiry, the address value inquiry, error codes, target frequency of the compressor, outdoor fan speed, the opening steps or the pulses of the EEV, the 4-way valve position, T3, T4, T5 temperatures, as well as your T2B temperatures, which we know is that average for those EXVs to maintain, and also the threshold on where it opens a valve or closes a valve based on that average. Okay, so depending on how you want to wire in, is going to give you different data on there. Typically, what I tell guys is if they're looking for a rule to split it up between what connection you want to use. If you're trying to test individual components of the outdoor unit, I suggest that you use the 5-volt DC test port plugin, because there you can get in and fire off individual components such as the compressor, the 4-way valve, the EXV, and verify that they respond properly from the signal sent from the tool. If you're trying to test a control board, whether it's an outdoor unit control board, indoor unit control board, indoor unit fan speed, you would want to use your L, N, and S. So again, this should be definitely something that you look at and decide, am I going to use my high power connection, or am I going to use my low voltage DC to individually test components from the outdoor board? Okay, so we know on here, this is your connection switch that you need to adjust on there. You'll have 4 sets of buttons. Of course, the arrows are pretty self-explanatory. As you go through different menus, you can use your up and down to navigate through those menus. Your red button is your return button, and your OK button is your accept or OK or select button for that particular menu that you're trying to get into. Okay, pretty straightforward. Nothing really too complex about that. Of course, you have any issues with something, you can always call me and bring your issue to me and we can work through it. So getting into features of the tool. So the first part of this tool is going to be your information inquiry. So this is to see the current running state of the equipment. This is sensors such as T1, T2, T2B, T3, T4, and T5, which if you paid attention from the last part that we were talking about as far as the advanced features and control, T1 and T2 are our indoor coil temperature sensor and our return air temperature sensor. T3, T4, and T5 are outdoor coil temperature sensor, outdoor ambient temperature sensor, and also our compressor discharge temperature protection sensor. So you can see all of that information. The biggest thing to understand on here is that this tool, because of where it comes from and where this equipment was originally founded at, is displayed in degrees Celsius. So you need to convert over whatever your reading is on there to a degree in Fahrenheit to make sure that we're reading it properly. The second menu on there is going to be your parameter setting. So this is where you can plug in with that 5-volt connection and adjust the target frequency of the compressor. Or for troubleshooting, you can essentially send a temporary control to the compressor to have it run off and fire and test to see if it's tripping off on a particular code, or just to make sure that it runs properly from the command sent from the tool. You can also do the same with the outdoor fan motor and the EXV position. Okay, and this is how we're going to test the individual components if you suspect one of being bad if you're using this on a troubleshooting scenario. You have a communication error analysis on here. So this is where you're going to use your L1, L2, and S, or your LN and S connections to perform a self-check on the tool to make sure that it's working properly, an online check to make sure that a unit, whether it's one or multiple, that actually is online and is responding. And you can check indoor and outdoor PCBs by wiring through an outdoor bus bar or an indoor bus bar to make sure that they respond from commands sent from the tool. So if you were troubleshooting, excuse me, if you were troubleshooting an indoor unit, this tool is essentially going to send a code and act as the outdoor unit and make sure the indoor unit responds. Vice versa, if you're using it to check an outdoor control board, the tool is going to act as an indoor unit, send a control signal to the outdoor unit board, and make sure you get a proper response back. And it's a really great way to narrow down whether you actually have a control board issue or if you're dealing with another factor that you need to focus on. Our final one on there is going to be our communication simulation. So this is going to be your indoor unit and outdoor unit inquiry, which we'll get into and we'll talk about here shortly. So first menu is going to be our information inquiry. So you'll see on here, when you go into the tool, you're going to power the tool on. When you get into the tool's main menu on there, I'm actually just going to back up so it makes a little bit more sense. When you first power the tool on, this menu right here is what you're going to see: the data inquiry, the running parameter setting, communication detect, so on and so forth. So when you power the tool on, you're getting into the information inquiry. Okay. Go ahead and select this by using your up and down arrows. You should start off as your basis on the data inquiry. So all you should have to do is hit your green check mark or your OK button to enter into that menu. Okay. Once you're in that menu, you can now use your up and down temperature arrows to navigate to different submenus within that menu. So you can see on here, you can have a fault inquiry. And again, unfortunately, this is not a history of error codes. It only displays active error codes. And that is a common request and something that guys wish that we had was a history of error codes, but it only displays active error codes in the system. Your second on there is your address number. This is something that you guys don't have to concern yourself with. If necessary, it's something that I can gain access or have you give information to me from so that we know what we're dealing with. But typically, this is not something that you guys will be getting into. The final one on there, which should be the first one that you actually start with, is your data inquiry. So once you want to get into this menu, you go ahead and hit your green check mark again, and you'll enter into the data inquiry. From there, you can get information such as your T1, T2, and T3 sensors. Now you can see on here, they're all displayed in degrees Celsius. Okay, so if you're only hooked up to the outdoor unit, you're not going to read a T1 and a T2 temperature reading. You're only going to read the sensors of the outdoor unit, which is their T3, T4, and T5 temperature sensors. Okay, you'll also see on here different temperature ratings for your drive board to make sure that it's not overheating. Your DC fan speed, which we looked at RPM, which is where we can verify that at. You'll see your PMV opening on there, 480 or 480 pulses. And you'll see different target frequencies, control frequencies, and run frequencies. And we talked about that at the beginning of this class when we were understanding target versus run. This is where you can confirm the information of the current running frequency, which you should see on the main board, and then more importantly, the control frequency of where the unit's trying to maintain at, or that target. I'm sorry, flip-flop that. Actually said that wrong. The control frequency is where it's currently at on there with the running, and then the target frequency is where it's trying to maintain at once it slowly gets those units to their set points and where that sweet spot of the system is. Okay, so now moving on to your parameter setting. So your parameter setting on there is going to be done with your 5-volt connection. So if we kind of backtrack a little bit just to clarify on the information inquiry. The information inquiry, you can get information off of the LN and S connection and also the 5-volt DC connection. It just depends on where you want to plug in. With this particular parameter setting, you want to plug in on the outdoor unit if you're trying to test individual components with your 5-volt DC connection. Okay, so when you plug in and get your screen all powered up, you use your up and down arrows on there to go to the running parameter setting menu and make sure that it's highlighted. You hit the green button to select that and get into that running parameter setting menu. And then from here, inside this menu, you'll see a setting target frequency, fan speed, PMV opening, a 4-way valve state. In order to change something, so if we were to change the target frequency on here, we'd want to go ahead and hit the green arrow to get into that. And you'll see from here, you'll see it's at 0.0. If you use your temperature, well, I shouldn't say temperature, but if you use your up and down arrows on here and increase this frequency, it will actually send a command. So you turn this up, let's just say we adjust it, hit this up arrow till it's at 30. We want to run it at 30 hertz. Okay. Once we go to the 30, we hit the green OK arrow to send the command on there, and you'll hear the system or the compressor try to start off. This is how we go in and individually fire off the compressor, the fan, the EXVs, and the 4-way valve. And this is the menu that we're going to get into to manually adjust those individual components in the outdoor unit if we suspect them of being bad and we want to test them. Okay, so again, we have the target frequency of the compressor, we have the outdoor unit fan speed, we have the PMV or the EXV or expansion valve opening, and we also have the 4-way valve state. So we can test all the major components in the outdoor unit, and this handheld controller essentially acting as the signal that's being sent from the indoor unit to the outdoor unit to turn it on. So we're acting as the operator or the brains of the operation by using this tool and individually testing components to confirm if they're working properly, or if we need to start troubleshooting them further and confirm that they are in fact faulty. So when you're going in the menu that comes with this tool, you'll see on here, it'll give you a certain range that is valid for whether it's not running at all or its maximum range that it can run. And this is just something you want to pay attention to on here, especially if you're trying to navigate through here and set different settings on here. Typically, I don't use this if I'm firing off individual components. I usually just kind of turn them up to a certain degree, let them run. But if you're trying to mimic a certain scenario, whether a fan speed's going out of control or a certain frequency the compressor seems to have issues or kicks off, this is certainly something that you want to have in your possession to know where you can adjust things, what the minimum and what the maximum is. Okay. And the most important part on here too, especially for setting the compressor target frequency, what we talked about in the beginning, is that is the sweet spot of the system. You'll see on here in cooling mode and heating mode, it has different minimums, maximums, and suitable ranges on there. So if for some odd reason you change something in the cooling mode to maximum or above, or the minimum or below, that is on you guys for changing that. And again, that's why I mentioned at the beginning of this. Typically, I haven't ran into a situation where, excuse me, adjusting the target frequency of the compressor was necessary. This is more so for just figuring out where that actual point is. And then, of course, if something does need to be changed on that, that is either going to be communicated and approved by myself or someone directly at the factory to make that change on there, of course, depending on the situation that we're dealing with. But they do list this manual in there for you to realize what a suitable range is. So if you're trying to adjust the frequency to a certain point, if you're testing an individual component, you want to make sure that you keep that setting point between the suitable range so you don't cause any harmonic damage from that compressor overspeeding itself. All right, so that's your basic 4 submenus on there. So let's get into the communication error analysis. So this is going to be troubleshooting those pesky E1 communication codes. Okay, so when you're testing this error code on here for the E1 error code, you can see on there on the pictorial, your test board is actually the service tool, and you're going to plug in on the L, N, and S to be able to test this. So as soon as you wire this L, N, and S to the bus bar, now you'll see on here these actually do come with female connectors that will plug directly in on the top side of the bus bar. If you don't want to use these on there, you're more than welcome to cut them off and strip the wire so it's there to get it underneath there. Of course, you want to make sure you have a good, secure electrical connection. So when the device is connected, you set your settings to your L, N, and S on your service tool. The device will immediately start carrying out a communication check for the system. So if you have an E1 code and you plug this on, well, you shut the power off, you plug this on to the bus bar, you power the tool on. After turning the system on, it starts getting and receiving different communication situations. So you'll get any of the 3 feedback messages after the check has been performed. Your first scenario is the tool comes up with an indoor communication fault. What that means is you either need to check the indoor unit or something within the indoor unit or the wire going to the indoor unit. Okay, this is oftentimes, especially in the summer, if you have a condensate pump that is broke through the signal wire and decides to fail, it will break communication. And if you're using the ductless service tool to troubleshoot that, this is most commonly the code that you're going to see on there, which would be an indoor communication fault. The second code would be your outdoor communication fault. So you either need to check something within the outdoor unit or a communication wire. This does not automatically mean to replace the board. You need to do your due diligence and make sure there are no loose signal wire connections on there or something on the board that might be smoking. You see it on the board confirming that it's not getting power, or it's getting power, but it's not powering on, which is why you have E1. Now, of course, that would be a board in that scenario, but don't assume that it's just a board. Do your due diligence and troubleshoot. Finally, your communication is normal. So if you have a scenario where you know you have a documented E1 code, the indoor unit's displaying an E1, the system's displaying an E1, and you get a communication normal, if that happens, that indoor PCB is faulty and will need to be replaced. Of course, in a multi-zone, you want to check individual zones on there to make sure that you know which one is coming back as communication normal and which indoor PCB may or may not be faulty. Again, this is not to say as soon as you get an indoor communication fault or outdoor communication fault that just replace the board. We still need to be service techs. We still need to do our due diligence and troubleshoot through the situation to make sure that it's something not external to the board. So if the board does get replaced, we're not back out there with the same issue again. Okay, but as a rule of thumb, this is how we're going to go ahead and just do a basic communication check to make sure that the system is operating properly. Or if we're on a service call, this is how we're going to go through and confirm where that actual E1 is present. So getting into here through your indoor unit, so this is going to be your self-test menu, your online detect menu, your indoor unit simulator, and your outdoor unit simulator. This is going to be done through your L, N, and S connection that you will receive with the tool. So when you power this on through your L, N, and S connection on there, you want to go down to your communication simulation tab and hit your green arrow to get into it. And you'll see in here you have these different menus: self-test, an online detect, indoor detect, outdoor detect. And depending on what you want to do is what menu or what feature that you're going to want to select on there. Okay, so getting into the self-testing menu. So the self-testing menu is to simulate an indoor unit to determine if that outdoor unit will respond and determine, more importantly, that the outdoor unit board is working properly. Okay, so we want to make sure that the outdoor unit is responding properly. So we're going to use this tool to act as a fake indoor unit to send a control signal to it and make sure we get a proper response back. Okay, so when we're using this feature, we want to make sure that we disconnect the signal wire from that particular zone that we're connecting to. So we only have L1 or L2 or LNN connected, depending on what type of power system that we're dealing with. Okay, now what we do want to do is there's a signal wire that hooks up to our indoor unit from the tool. We want to have our L1 and L2 connections from the tool connected and piggybacked off of the L1 and L2 that's currently on the bus bar because we need to power the tool. We're disconnecting the signal wire that actually comes from the indoor unit, and we're wiring in our signal wire from our tool to the signal terminal on the bus bar. Okay, once we have that wired in, we're going to go ahead and turn on the unit. We're going to go to our communication simulation menu, enter into there, select self-test. Okay, once you get that self-test menu on there, typically it takes about 10 to 15 seconds on there, and it will say either the device is communicating properly or that there is an issue. If there is an issue, this could be further credibility that there actually is something going on with the outdoor board, which could be the reason that you're out there. Or if you're doing this from a preventative maintenance point of view, you can go through individual indoor units and make sure that everything is responding with the board properly. But chances are, if you're doing it on one zone, the other zones are going to be communicating properly. Otherwise, every one of those zones would probably have an E1 issue. But again, this is more so on the service side of things, but you're always more than welcome to use it on the preventative maintenance side to really be thorough. We have our online detection feature on there. And again, this is in the communication simulation menu by selecting the online detection. So what this mode is used, it's used to check if that indoor unit is responding to a signal sent from the service tool to the corresponding indoor unit. So by using this feature, you can confirm an E1 communication code, which can be caused by various things. Of course, we want to start simple. We don't want to start crazy and start thinking algorithms and all this other crazy stuff that's causing E1. We start basic. So this feature is going to be used on each affected port in a multi-zone system, or if you're dealing with a single zone system, just that one particular indoor unit that's causing E1 code. Okay, so with that online detection, again, you want to hook up to the outdoor unit, L, N, and S. And by using the online detection, once you get into that submenu, once you're in the online feature on there, go ahead and press your green check button on there. And essentially what it's going to do is confirm that the indoor unit is online and is responding properly from the tool that you're using to simulate the outdoor unit to verify that it is working properly. Again, tool is simulating an outdoor unit, sending a signal to that indoor unit to confirm that it's talking. Okay, just like we did on the previous feature, except now the tool is mimicking the outdoor unit, sending a control signal to the indoor unit. And you can do that on each indoor unit to make sure that the indoor units are responding. Your communication simulation. So with the communication simulation on there, you can simulate different scenarios that you want to test the individual indoor unit. Okay, so in this case, we're looking at our indoor unit simulator. Okay, so just to rewind on here, when we're going to our main menu, this is still in the communication simulation menu. You just need to select either indoor unit simulator or outdoor unit simulator. So for the indoor unit simulator, this is going to be for that L, N, and S connection only. And of course, we know that S wire must be disconnected at the indoor unit that comes from the outdoor, and we wire in our signal wire that comes with the harness for the LNS connection on the service. Now with this, we can make changes to the mode, the target frequency, the indoor fan speed, and see an accurate T1 or T2 coil temperature. Okay. On the high wall units, the 40 MAQs, I personally wouldn't suggest doing this because they have an advanced feature on there that you can use the display on the unit itself to actually see those T1 and T2 values without wiring in this tool. But this is certainly great to have for a ducted floor console or cassette style unit to get that accurate information. Okay, but these are some of the features that we can get in there and simulate and test fire to see if a fan motor is responding or to see if a temperature sensor is reading properly within the range that it should be. And just as a reminder on there, they read out the temperature sensors in degrees Celsius. We need to convert over to Fahrenheit. Okay, again, with the indoor unit simulator, you need to disconnect the signal wire from the indoor unit and connect the signal wire on the wiring harness from the service tool itself that we're using to connect. Okay, with the outdoor unit simulator, this is going to be done by using that 5-volt DC connection. And again, this is the one where you plug it in on the test port pin, and you can access the mode information, the running frequency of the compressors, target frequency. You can get ambient temperature, you can get your outdoor coil temperature, and you can get your discharge temperature to verify that those sensors are also reading properly. And just like we did on the indoor unit side of things, remember that the temperature sensors are in degrees Celsius. We need to convert over to Fahrenheit. And of course, typically the rule of sensors is plus or minus 2 degrees for a sensor to be considered working or reading properly. So getting into the troubleshooting on here. So one thing to note, and I always say this in my install and service classes on there, is that you always want to make sure that you're looking at a code menu like this, and you're looking at the appropriate device. So you don't want to take an error code that's on a wired wall controller and use the indoor unit error codes as a basis to confirm what an actual code means. So basically what I'm trying to tell you is that the service manual that comes with the tool is where you need to verify if you're getting an E5 or an E52 or an E54, what that actually means. So an E54, for example, on the tool would be a compressor discharge temperature protection. So we talked about that. Okay, well, let me go see what that T5 is reading and make sure that, hey, is the sensor out of whack, or am I actually dealing with a scenario where the system couldn't throw countermeasures to correct the overheating of the sensor, and I need to see what's going on. Do I have a dirty coil? Do I have an outdoor fan motor that's not working? Do we have a valve issue? Again, don't take the E55 and look in the indoor unit service manual, because you're not going to find it and it's going to confuse you. So you want to make sure if you're reading the code on the tool that you use the tool's error code list to make sure that it matches up and confirm what that code is trying to tell you. Now, for example, codes that kind of stay the same throughout would be an E1 code. We know an E1 code on the indoor unit is a communication issue. Well, on the tool, it's also a communication issue as well. But the biggest thing out of that is just making sure that you're using this error code list, if you have an error code on your tool, to make sure that you're getting the correct diagnosis of what's going on with the system so that you're not chasing the ghost code. Okay, and you can see on here, there's a bunch of different codes that will come up depending on if you have various situations. What you'll see on there, the code will actually appear on the tool, followed by a brief explanation, which they have listed here of what's going on. So chances are you're probably not going to have to use this menu, but it's definitely something that I wanted to encourage you guys to become familiarized with, because with each different device comes its, each different check codes on there that we need to confirm that we're reading correctly. Okay. So that's what I had for you guys for the ductless service tool training. Hopefully you took something out of this. And just as a reminder, since this is a pre-recorded class, you are now available to buy the service tool, but this does not count towards training hours as far as the CFAG credit goes on there. You either have to be in a live class or, of course, attend a live online class. So if you guys have any questions on anything, please feel free to reach out to me. I'm actually supposed to have a slide with my contact information on here. Unfortunately, I don't think that I put it in. So my direct extension here at Standard is extension 129, and then the phone number for the office is 412-920-6505. And you can always shoot me an email. My email is tmay@stdair.com with any questions that you might have. And again, thank you guys for coming. Hopefully you took something out of it. Look forward to working with you in the future and growing your ductless success with Carrier. Thanks, guys.